Huyen Pham from Ecole Polytechnique, and he's going to talk about optimal transport for generative diffusion modeling, bridging Schrödinger and Bass bridges.
Okay. Thank you, Jose. So first, let me thank the organizers, so I see Yuan, Yufei, and Sam for organizing this workshop and yes, bridging people from different community, machine learning, applied mathematics. I think it's a great initiative. So I see, as you see in the title of my presentation, so I am also try to bridge. So here I bridge Schrödinger and Bass, who gave the name, in fact, to two class of important class of optimal transport. And so the motivation here is for generative modeling. So this is based on joint work with several people, so some researchers in the industry, so Pierre will aborder le pair. So Otman Mazar, who is ending his postdoc at my former place, Paris Cité, Nizar Touzi, now NOU, and Alexandre Alouadi, who is a PhD student, okay, working both at BNP Paribas and at Polytechnique. Okay, so as you know, in generative modeling, so the central question is how to generate new data that looks like very much to what we observe in the real world. Okay, so the goal is to produce realistic samples, okay, of complex distributions. So, for example, image or molecule or financial time series. And so a unifying way to think about this model, okay, is through the lens of property mass transport. Okay, so think about you start from some initial distribution, so typically a simple Gaussian distribution, and you want to transport to a more complex distribution. Okay, so image, molecule, etc. And so the modern generative modeling, okay, is precisely, okay, the construction of such dynamic map, okay, and so you can so the transformation can be either deterministic, okay, and so in this case you have normalizing flow matching, rectified flow, and so you have maps which are governed by OD, or the transformation, the transport can be stochastic. Okay, and so in this case, you have score-based diffusion model. So in fact, here you have two maps. So one map from the image data to the noise, and the backward process from the noise to the image. Bridge matching, or recently stochastic interpolant. And so here you have a model governed by SD. And optimal transport provide, in fact, a mathematical way to construct in optimal ways such transport, okay, grounded in a variational principle, okay, in contrast to rather ad hoc interpolation that you can have in normalizing flow, etc., stochastic interpolant. And so among the class of optimal transport, there is one very important theory, which is a Schrödinger bridge. And so what is a Schrödinger bridge? So it consists in searching among all diffusions that match your distribution, the one closest to the Brownian motion. Okay, so in the sense that you want to minimize the kinetic energy of this diffusion. And in fact, this is entropic. Another alternative way is to view as entropic optimal transport, in the sense that it's minimize the KL, the Kullback-Leibler divergence, with respect to the Wiener measure, while enforcing the marginal constraint. And it has a property that if you look at the optimal diffusion law, okay, it can be disintegrated into an optimal coupling, so from the static optimal transport, okay, with entropy, and between this optimal coupling between the target, the initial and target distribution, you have the Brownian bridge, okay, to connect the 2 points. And moreover, what is nice with the theory of Schrödinger bridge is that you have an explicit optimal drift, okay, which is written in a score form, in the sense that it is the gradient of a log density, and this density function h, okay, satisfy a backward heat equations, okay, with some terminal condition h capital T, okay, given from the Schrödinger system, so also known as the sinkhorn. So you have two potential corresponding to the two constraints, so h capital T and nu zero, okay, given by this system. So it means that the potential ht multiplied by nu t. So what is nu t is the law of the Brownian motion, starting from the potential times 0. Okay, so satisfying the Fokker-Planck equation, and you have to match with your target distribution, and you have a similar equation at time 0. Okay, so this is the Schrödinger or sinkhorn system. And okay, and so based on this theory, okay, you can now several people have applied this theory for the purpose of generative modeling, and so this means that given sample of mu0 and mu-t, okay, you will learn your solution. So in other words, you will learn your drift, you estimate your drift, and then given out of sample of mu0, okay, you will simulate your diffusion Schrödinger bridge in order to generate new sample of your target distribution. And so the implementation can be done with a recent competitive solver, which are scalable in high dimension. So recently, there is an iterative proportional fitting, which is a kind of extension of sinkhorn algorithm, iterative Markovian fitting, and very recently, the light Schrödinger bridge matching. So all this method, this solver, estimates the score drift by denoising score matching using simulation of the Brownian bridge. But the advantage of the light Schrödinger bridge is that it only uses one single iteration and no neural network, so a very simple parameterization to train, okay, in contrast to the EPF or EMF algorithm. But notice that in the theory of Schrödinger bridge, okay, the volatility is fixed. Okay, so it is one here, but it could be simply a constant. And so the question that we want to address here is, okay, can we also control the noise? Okay, so I will give you the motivation to control the noise. So in other words, to have also random volatility. And so the question is now, okay, how can we switch from the Schrödinger bridge, okay, to the Bass problem? So in Schrödinger bridge, as we have just seen, okay, you control the drift, okay, in order to be as close as possible to the Brownian motion. Okay, and at the opposite case, the Bass problem, here so it's a Martingale optimal transport, so the drift is equal to 0, okay, and then you are allowed to control only the volatility. And so here the aim is to unify both this theory, okay, through a single principle. And so the motivation is that we expect to be able to handle more general distribution, okay, beyond the assumption in Schrödinger bridge, so in particular to deal with heavier tail distribution. And for the purpose of generative modeling, okay, we expect by incorporating a random volatility to have more diversity in the synthetic samples, more distant data distribution, okay, from between mu0 and mu capital T. And also, if you think about application to finance, okay, it is natural to introduce random volatility if you think about financial time series with stochastic volatility. Okay, so let me now, so the rest of the talk will be divided into two parts. So I will present the theory of Schrödinger-Bass bridge, and then the application to the generative modeling. So the Schrödinger-Bass problem is formulated as follows. So given the fixed initial and target distribution, so the aim is to minimize over now both the drift and the volatility, okay, a quadratic cost. Okay, so as before, you have the kinetic energy on the drift, and now you have a penalization of the volatility with respect to the identity. And so we call by PSB the law of such optimal process if it exists. Okay, so first you can notice that at the limit, okay, you retrieve, okay, on the one hand the Schrödinger bridge when beta goes to infinity, because in this case you constrain sigma to be equal to identity. And at the opposite case, when beta goes to 0, in this case, you force alpha to be equal to 0, and then you retrieve the Bass problem in martingale-Huyen transport. Okay, and so now we have this flexibility through this parameter beta. Okay, and so this is what I show in this graph. So this parameter is kind of tuning parameter, okay, where you can switch from the Schrödinger bridge, which is entropy optimal transport, okay, and to the other side, which is the Bass, okay, which is martingale optimal transport. And from the perspective of generative modeling, so when beta is large, okay, you maybe more obtain something which is you have some fidelity with respect to the samples. Why with beta small, okay, when you go to the random volatility, okay, you can expect to have more diversity in the samples that you will generate. Okay, and so now let me give you directly the result, so the general result, okay, which is that you can view as the extension of the Schrödinger system. Okay, so we call it a SBB system. Okay, so it's kind of Schrödinger Bass bridge synchron in the potential form. So it looks like similar to okay, to what we have viewed in the Schrödinger system. So now, except that on the left-hand side, instead of matching mu t, what you match is a transport of mu t, okay, by means of a transport map, okay, which is explicit in terms of the density function h, okay, and which is a gradient of a convex function. Okay, so phi is a convex function, and so you take this transport map, so it is an increasing function, and then you match the density and the laws of Brownian motion to the transport of mu t by the transport map yt. Okay, so this is the main result, a main theoretical result. Okay, which so before I give the implication for in terms of the corresponding diffusion process, let me just notice that, okay, at the limit again, okay, you retrieve on the one hand the Schrödinger system, because in this case the transport map is simply the identity, and when beta goes to 0, you retrieve the Bass system, okay, which leads to the martingale synchron algorithm, okay, which has been studied a lot in calibration problems, so for example by Huyen and Ecole. And also, what is nice also is that when both mu0 and mu t are Gaussian, then it turns out that the solution to the system is explicit. Okay, so in the sense that the log density is quadratic and the transport map is affine. So in this case, we extend the results, the recent results that have been obtained, okay, in the Schrödinger case. Okay, so let me now give the implication of these results in terms of the diffusion process. Okay, so for this, okay, I define the process yt, okay, which is the transport of the process x by the map y, okay, and the change of measure, the change of measure given by this inverse of this density process. Okay, and so using the Schrödinger Bass bridge system, okay, we then show that the process y here is a Brownian motion under this change of probability measure. Okay, so which means that xt, which is the inverse of yt by the inverse transform map, is what we call a stretch Brownian motion. So it's a monotone function of a Brownian motion, okay, with constraint marginal. Okay, and moreover, the process y here is in fact a diffusion Schrödinger bridge, so it has this fixed constant and score drift term, which means that in fact the solution of the Schrödinger Bass bridge can be viewed as a Bass transport of a Schrödinger bridge. Okay, in the sense that, okay, what you can do is you construct the Schrödinger Bass bridge solution in two steps. So first you build a Schrödinger bridge in the y space, and then you transport back, okay, via the Bass map, okay, to get the solution x. Okay, and if you alternatively, okay, if you work directly on the x space, you have an explicit formula expression for the optimal drift and volatility in feedback form, as follows. Okay, you have here again the score, and here's the Hessian of the function phi. Okay, so this is okay the theory for this for the solution to this Schrödinger Bass bridge. And now, okay, second part of the talk. Let me give the application to okay, so for our initial motivation, so generative modeling. Okay, so now given the result I just showed you, so we see that there are in fact two sampling methods for generating optimally mu capital T. So either okay, you simulate directly in the X space your diffusion process, okay, using the analytic expression of the score drift and of the volatility, so that okay, you will generate by construction mu capital T at the end. Or second method, okay, you generate the Y process as a Schrödinger bridge, as a diffusion Schrödinger bridge, okay, but now with endpoints which are not mu0 and mu t, but the transport of mu0 by Y and the transport of mu t by the transport map yt. And then, okay, you reverse back to get X capital T by taking the inverse transport map, so that again, by construction, you will sample according to mu t. Okay? And so, in fact, this is the second method that we shall use because we shall realize, in fact, on the recent advances for simulating the Schrödinger bridge. Okay, so this gives rise to what we call the light Schrödinger Bass bridge matching. Okay, so where again we exploit the fact that the solution is a Bass transport of the Schrödinger bridge. Okay, so now first step we have to simulate the Y process, the Schrödinger bridge, but between two distributions that you don't know, because it is expressed in terms of a transport map, okay, that you have to estimate, okay, in terms of the score. Okay, so this means that naturally what you do is you iterate, so you start from some score, 0, for example, equal to 0. Then at iteration k, you draw endpoint pairs, y0, yt, according to this distribution, mu0 transport by the transport at iteration k, and similarly at time capital T. And then, okay, you use, for example, your light Schrödinger bridge matching to to simulate Y and then update the score, okay, and then at final iteration, okay, you generate out of sample of mu t, okay, by using the inverse transform map. And in practice, okay, it's only 5 iterations is enough to obtain a good result for this methodology. And again, I insist that in this step here, okay, it's a very light algorithm because you don't need to iterate. Okay, you just use a single parameterization of your score. Okay. Okay, so now let me give you some numerical experiment. Okay, so first I would like to start with some quantitative comparison. So we use a two-dimensional test, okay, which has been used by the Mila group by Yoshua Bengio. And so the aim is to see, okay, the quality of our model, okay, by varying this tuning parameter beta. Okay, and so we use 3 training data sets. So in the first training data set, okay, so we want to transport a Gaussian distribution in blue, okay, to a half moon distribution in orange. Okay, and so here the different panel correspond to different value of beta. Okay, and so here, okay, the test is about for generating starting from a moon distribution, half moon distribution, to 8 Gaussian distribution in orange. And here, okay, from Gaussian distribution to 8 Gaussian distribution. And so we perform the result, okay, for different value of beta. And for the different value of beta, what we do is that we compute the Wasserstein 2 distance, okay, between what we obtain and the real one. Okay, and so the lower the better. And so you see that for most of the experiments, okay, the lowest value you obtain when beta is equal to 100, okay, and sometimes for 10. Okay, so this is why we do this in 2 dimensions, because in 2 dimensions you can compute very explicitly the 2 Watershed distance. And so here it's more, okay, this table shows quantitative state-of-the-art comparison. So here we just took the result obtained by different methods. So here, I don't know all this method, but there is a Schrödinger bridge using EPF, EMF, optimal transport, rectified flow, flow matching, etc. And for each of these data sets, okay, we took the table from the Miller group with the Watershed distance. And here is the result, okay, that we obtained with our algorithm. And so what you can see is that, in fact, the Schrödinger Bass bridge problem, okay, achieves the best performance among all this algorithm, at least in this 2-dimensional benchmark. Okay, so this is for the quantitative result. So now more, okay, qualitative. Yes.
The amplitude distance here is computed by entropic limit, or?
I don't know. I think it's using maybe Synchron algorithm to. Yes. And so here it's a more funny example. So here we want to transport image of adult to child, okay, both for female and male. And so here is a x0 distribution of the woman. And then we transport to y0, okay, and then from y0 to y1, okay, this is a Schrödinger bridge, okay, so it's still not yet a girl. And then the last step is to transport back, then you have a girl, okay. And here similarly for a man, okay, you transport from x0 to y0, Schrödinger bridge, not yet a boy. And last step, okay, it's more younger. Okay.
What's the dimension here?
It's a dimensional image. So in image, you know that first you compress and then you decode. And so here, yes, for value of beta 5 and 10 for the male.
Intuitively, why they have different beta?
Why they are?
They have different beta.
We choose different beta. It's our choice. We just want to test for different beta.
That's the best.
Sorry?
Those are the best.
No, I don't know if it is the best. We just test by chance. Because best is difficult to check in terms of visual quality. You can see on table on Watershed distance, but for image, okay. So it's why it's just qualitative result. And so it can be also done with, now if you start from noise, okay, like in score-based diffusion model, so you start from noise and you want to generate image of a child. And so here, the noise, and here is just 3 representative samples of a child. Okay, so you see that here there is some kind of diversity in the image of the child in this picture. Okay. Okay, so I have some time. So now I would like to see, okay, how we can adapt to extend, okay, this theory to time series distribution. So in particular, motivated by application in finance. So for time series, the problem is adapted as follows. So now, the distribution that we want to generate is a joint time series distribution, okay, that you observe at, say, n times, t0, tn. And so you want still to construct a diffusion process by controlling the drift and the volatility. Okay, so the same cost, same transportation cost, but now the constraint law is on the joint distribution. So you want to find okay, a diffusion process which interpolates your time series distribution, okay, instead of matching the marginal low at 0 in capital T. Okay, and so this is what we call SBBTS for time series. In the case where beta is equal to infinity, so in other words, the case of Schrödinger bridge, okay, was introduced in my paper with Mohamed Amdouche and Pierre-Henri Laborde. So here it can be viewed as an extension in order to incorporate random volatility. Okay, and so in fact, this problem, okay, can be reduced sequentially to a Schrödinger Bass bridge problem, okay, by simply observing that if you disintegrate your joint distribution, okay, in terms of conditional distribution, then you can solve your optimal interpolation time series sequentially by forward induction by solving your Schrödinger bridge on two consecutive time steps, Ti and Ti plus 1, by transporting a Dirac at xti to the conditional next step low, the conditional with respect to the past of your time series. Okay, and so this is our way. So in this case, we can exploit what we did for the one period case. And so, so here I show you some results. So this result is to test, okay, the robustness of famous stochastic volatility in finance. So we take a Heston model, okay, with there is 5 parameters in the Heston model, and what we do is we simulate, okay, data from the Heston model, okay, but not with fixed parameters, because in practice the parameter in Heston model varies. Okay, so we simulate a lot of data of the Heston model by varying the range of the parameters, okay, in this blue term. So the parameters vary in this range. So we vary all the parameters, the vol of the vol, the volatility, okay, within a range, because we don't know in practice what is the exact value of the parameter. And then using this simulated data, okay, we synthesize the Schrödinger bridge time series and the Schrödinger bridge Bass time series. And using this synthetic data, okay, we estimate the parameter by maximum likelihood. Okay, and so here you see in this plot, okay, the distribution of the, for example, of the vol, okay, using so here for the data distribution, for the Schrödinger bridge time series, and for the Schrödinger bridge Bass time series. So you see that the fact that we incorporate random volatility, okay, is much more robust that if we only use constant volatility, because in the case of constant volatility, okay, we do not really match the real distribution of the parameter. And similarly, it's even worse for the estimation of the parameter rho. Okay, so in other words, okay, by incorporating a random volatility, okay, you are able to have a more robust estimation of your parameters.
So,
yes.
I don't understand. So there are two ways of interpreting this. Right? I mean, at least. So one way is you give me a time series of size n, right? Say, for example, of a day.
Yes.
And you give me a month, so 30 days of this time series.
Okay.
And I want to generate day 31.
Okay.
That's one interpretation. The other interpretation is you just give me the full time series, like there are no independence in days, like the whole thing. And I want to estimate, and I want to feed a model for the transition distribution of the Markov process, which is, that one, sample from the I to the I plus 1. Which one of the two are you doing?
So it's a circle method. So here, here is not a prediction. So here, I want to produce other sample of the time series, and from these samples, I want to estimate the parameter.
So a competing method would be just, I know that a Bass martingale. So you basically have a parametric model, which is a Bass martingale, which are parameterized by the gradient of some function.
Yeah.
You do maximum likelihood that with Brownian motion as your driver, and you just fit maximum likelihood to this,
Yeah.
to the data. Is this?
No. So here,
Because that's a competing.
it's a different method. So here we simply, we have a sample of our model, generative model, and based on this sample, we just apply, maximum likelihood, to estimate the parameters.
Okay. Yeah.
Okay, so this is one test. The other test is maybe more related to your first use of time series. It's because one case use of time series is, of synthetic data is to get data augmentation. Okay, in particular, data augmentation can be used for many things, but in particular, it can be used for forecasting task. And so here we want to use a real-world forecasting task. Okay, and so the real data set, it's come from the Apple stock. Okay, and so the goal, as in many banks and hedge funds, is to predict the sign, of the next return, given the past value. Okay, and so this is we do this by training LSTM neural network. Okay, so in other words, what we get is the output. Okay, we give you the estimated probability of positive next return. Okay, so it is a number between 0 and 1. So it gives you the probability that you go up, or go down. Okay, and so the goal, is to capture the predictive signal. Okay, so in other words, the alpha, which you can measure as a deviation, between the two directions of the next return, so 0 or 1, 0 if it decreases, or 1 if it increases, and the predicted direction, that you derive from your training LSTM. Okay. Then to train, and the data that we use, to train this LSTM, so we split the data, 10 years of training data before the COVID, validation set, and test set. Okay, and so then we produce our synthetic data, using both the Schrödinger bridge time series or the Schrödinger Bass bridge time series, and we also eventually mix that with the data set. Okay, and so the performance evaluation is obtained by computing the classification accuracy. So in other words, you compute over your evaluation set, so the validation or test set, the frequency that you have predicted correctly the sign of your next return. Okay, so as you know, next return you are mostly noise. So in general, you expect that this accuracy is more or less close to 0.5, because with 1 chance over 2, you will miss the real prediction. Okay, and so this example, so here is, as I say, if you only use data in general, what you obtain is something close to 0.5, and you see that with the Schrödinger Bass bridge time series or the Schrödinger bridge, you are really able to improve, the accuracy. So it's rather significant. Okay, so it's much larger than 0.5. Okay, so this result illustrates, how it is useful to get data augmentation in order to have a better prediction of your next return. Yes.
What's the frequency of the data?
Sorry?
What's the frequency of the data? Is it daily?
It's daily, yes. Daily data.
But on the test, which is the real...
Yes, on the test, yes, it's the Schrödinger bridge time series slightly better than the Schrödinger Bass bridge. We don't know why, but it's, yes, a little bit better.
It also seems that if you're using not only the synthetic data, but the synthetic data plus the true
yes,
data,
it's not good.
Performance drops.
Yes. So it's.
What is that?
For the moment, I don't really have interpretation. So it's just results that you obtained last week. So, but yes, that's true that we are surprised that when you mix synthetic plus real data,
How big are the sets? Do you know how many synthetic
data? I saw half, I think. Half, I think. Okay, so let me now conclude. Okay, So what we did here, so we have provided a mathematical unification between Schrödinger bridge and Bass problem, okay, via the volatility control, so which leads to what we call Schrödinger bridge Bass problem. Okay, so it's this sum up with this figure. So start from Optimal transport, with entropy. Okay, you get the Schrödinger bridge. Okay, at the limit, you get the Bass problem, so Martingale limit, and between, okay, you have some kind of unification, okay, between Schrödinger bridge and Bass. Application to generative diffusion model from an algorithmic point of view, the light Schrödinger bridge matching is very powerful, so it leverages the recent advances on diffusion model. In practice, I show you that for two-dimensional metrics, it's rather competitive. For image, okay, it's the fact that you are able to tune the parameter beta, okay, give you some control on the diversity of your image. And we have, I think, promising time series in finance, okay, both in terms of prediction and robustness. Some extension. In fact, this theory can be extended to soft law constraints. So meaning that instead of matching perfectly the data distribution, okay, you can do a soft law constraint. Okay, so by meaning that you can penalize the distance between the law of xt and mu t. Okay, so this is something, for example, that has been done recently by Huyen. And so here it can be done similarly. Okay, so it's fine. It's almost the same system as Schrödinger bridge. So, but typically, if you take, for example, F divergence, it's easy to compute the solution to this problem. Another extension that can be done is to extend to jump process. So here we use diffusion model. Okay, so the noise is governed by Brown motion, but you can also add jump process, which can be useful, especially if you have in mind the modeling of Hawkes event data, time data, etc. So this is joint work with Stefano De Marco and David Nezani. Okay, so I think I will stop here. Thank you.